Today we're going to talk about scientific notation. So what is scientific notation? Well, it is how we write really big numbers and how we write really small numbers with powers of tens. So really big numbers, so numbers that we would see in maybe astrology, in astronomy, things that are really big, distance between planets, really, really big numbers. In reality, anything that is greater than 1 is considered a big number in scientific notation world, but really it's more used for things that are really, really giant, how many miles away different things are as far as planets go up in outer space. Really small numbers, this is where we see in chemistry, we see in biology, we see things with lots and lots of zeros right after a decimal point. The really, really, really small numbers, again, basically our really small numbers are really kind of anything that is less than 1. So how does the rule work for this? So first, we always have a number that has to be 1 or greater, but less than 10 as the beginning part of our scientific notation. Then we always have multiplication of some base 10. And the base 10 is always raised to an exponent that is always the integers, either a positive number or a negative number. And we'll look at a few examples as we go. But basically, just to kind of review a little bit of that. So that always looks like this. There's a number in the front. This number is always 1 or greater, but less than 10. So the highest it would be is 1.9999 repeating. There's always times 10. There's always going to be times 10 in scientific notation. And then this base 10 is raised to an exponent that is either a positive exponent or a negative exponent. Now, as you can see with this chart over here, if the number of the exponent is a positive number, then that is going to be our really large numbers. If our number is between 0 and 1, then that would tell me that my exponent is negative. Now remember, we just talked about negative exponents do not make my answer negative. What it's going to do is take that base 10, which is 10 over 1, and flip it upside down to be 1/10. So all of our really small numbers, and again, we're going to see a few examples in a minute, that are between 0 and 1, and they are going to have a negative exponent on that 10. So let's just see a few examples, and maybe they'll start to kind of clear up a little bit of confusion that some of us might have. So this first one, 19,000. We want to write this in scientific notation. Well, they've done a little bit of this for us already. So notice what they've done right here is they've taken my decimal point, which is really right here, and they've moved it all the way back to between the 1 and the 9. We have to do that because remember up above we just said that this first number has to be between 1 and less than 10. If I put the decimal point anywhere else over here, that number on the front would be too big. So 1.9 is how we would start. We said it's always times 10. Now we want this to be the same value as this because of that equal sign. So let's think about what this will do. The decimal point was right here, and it's been moved 1, 2, 3, 4 places to get to that 1.9. Now again, this is one of our really big numbers. So if I want to turn 1.9 back into 19,000, I'm going to have to move the decimal place 4 to the right. So there is my answer, 1.9 times 10 to the 4th. Number 2. Number 2, again, the decimal point has been moved. It was sitting right here. It's been moved all the way back here to start scientific because it has to be between 1 and 10, which is 3.4. So again, it's moved 1, 2, 3. Any number that is one of our greater than 1 numbers is going to be our bigger numbers, which is the positive exponents. So that is 3.4 times 10 to the 3rd. Moving on to the next one. The next one, we now have one of those numbers. This is between 0 and 1. This is one of our really tiny, tiny numbers. So again, we have to take this decimal and put it between the 4 and the 7 to create this first number that's 1 or greater but less than 10. This time, we're moving it. Still 3 places, but notice how this time we moved it 3 the opposite way. So what happens on this one is, this decimal does still move 3 places just like this one. But this is one of our big numbers, so it's the positive exponent. This is one of our tiny numbers, so this exponent is now going to be a negative 3. Remember, negative exponents don't make the answer negative. They are actually turning this 10 into 1/10, which turns into division, which is why it gets smaller and smaller from 4.75. Same idea happens on the next one. The next one is one of our little small numbers, so that tells me when this is 0 is in front, this will be a negative exponent. 0 in the front, this will be a negative exponent. So 2.37 is the only place it can go to make this first number between 1 and 10. It has to move how many places? 2 places, but it's going to be our smaller numbers, so it's a negative 2. Try these other 4 here real quickly. I'm going to pause the video, and when I come back on, you'll see the answers. So I would pause it just so you can try them and see how you come out. So how'd you do? There are the answers. You'll notice that we see some 5s and some negative 5s, but you want to make sure that you make sense out of it. Just kind of going through these real quickly. This 5 is where the decimal place would have to be to make this number between 1 and 10. And then I'm moving it 5 places, and it has to be positive because this is a much bigger number than a 1. This one is between that 0 and 1, which means that it's going to be a negative exponent. And again, to get the decimal place, 1, 2, 3, 4, 5, it has to sit between the 9 and the 7 to make 9.7, so it's a negative 5. Then when I look at the next 2, I get the negative 4 and I get the positive 5. Now any of these you can check as you go, because I can take this number, for example, and say if I turn this into 10,000, which is what 10 to the 5th is, and multiply it by this, I am going to get the 524,000. So you can always check it. Now we want to be able to write some of these on our own. So I'm just going to show you a couple real quick on my own, and then I'm going to have you go ahead and try them. So looking at this first one, I need my first number, remember, to be between 1 and 10. So the only way that that would happen is if I first have 7.3. So hopefully we can all see that if I put it where it starts out here, if I put it here, it's now still too big, still too big, still too big, still too big, still too big. Perfect. 7.3. If I went this far, it'd be 0.73. This has to be between 1 and 10. Then, as we've been saying, always times 10. And now I want to think, well, what do I have to do to get this decimal place back to where it started? So if I look at my decimal point, I've now moved it there. I need to multiply it 1, 2, 3, 4, 5, 6 to go forward. And it's a big number, so it has to be a positive 6. Looking at the next one, the only place that I can put that decimal is between the 6 and the 3 to make 6.3. Always times 10. This is obviously one of our bigger numbers, so I look at the decimal between the 6 and the 3, and I have to move it how many places? 10 places to get it to the very, very end, and it's a positive, so it has to be a positive exponent because it's one of the big numbers. The next one, we see 0 point, a bunch of zeros. That tells me that we're going to have a negative exponent. The only place that this decimal can go is between the 5.26. That gives me a number between 1 and 10. Multiply it by 10 always. And then I look at how many places to get those two to match up. So I'm right here. 1, 2, 3, 4, 5, 6 places. But remember, we're talking about one of our negative exponents because this number is between 0 and 1. That's one of our really, really small numbers. Lastly, the only place the decimal can go to get that first number to look like a number between 1 and 10 is between the 2 and the 4, which is 2.42. Always times 10. Again, this is one of our bigger numbers, so it's going to be a positive exponent. And when I move my decimals back it's a positive 6. The next three questions are saying, is this number written in scientific? Okay, so remember, what does it mean to be scientific? So scientific means that the first number has to be between 1 and 10. That is true there, so that's good. The second thing it says, it has to be times 10. That's good. And the 10 has to have an exponent, either positive or negative. So yes, we would say this first one is definitely fitting the form. The second one, if I did 8.3, that's good, times 10, that's good, to the 7th power, that's good, we're good there. The next one, 0.9, is that between 1 and 10? No, not really. So this one right away falls on its face. Also, times 10, no, it's not times 10, it's a base 7. So there's actually two reasons why this one falls apart. It is not scientific just because it might look like exponents and looks like multiplication. It has to have a base 10, and that first factor or number has to be between 1 and 10. So next we want to look at the exponents and how it helps us decide what to do. Well, we've been kind of talking about this. If I have a negative exponent, that really means we're making that base 10 turn into 1/10. And when I multiply something by 1/10, really what I'm doing is dividing by 10. So when I see something with a negative exponent, that is telling me move my decimal to the left. So I'm taking my decimal point and I'm moving it to the left that many places. Secondly, if I see an exponent that's positive on those base 10s, that's basically saying every time you multiply, you're adding one more 0 or one more place value, which is really what we're doing. So the decimal place is going to move to the right for each of those exponents. So here's a few examples writing in standard form. Remember, standard form just means how we normally would see numbers with zeros and commas. So let me just talk through a couple of these first. This is scientific notation. We have a number between 1 and 10. We see times 10, and we have an exponent. This one happens to be positive. So that tells me this number is going to be one of our bigger numbers. And again, bigger numbers in scientific means greater than 1. So also what I want to notice is, because we are talking about a positive 3, from above we saw the positive exponent means just move the decimal place to the right 3 places. So this decimal place, this is telling me if it's positive, I'm just going to move it to the right. So 3.5, if I was to move it 3 places, there's 1, there's 2, there's 3. Now notice I ran out of numbers from that 3.5, so really all I'm going to do at that point is I'm just going to kind of go in and fill in a couple of those little scoop things that went by. And now I have my actual answer, 3,500. On the next one, again, positive. That tells me that if it's a positive exponent, I'm going to be moving my decimal to the right. So I'm going to take my 2.48 and I'm going to move it 6 places. So 6 places, first 2 are going to get me around the 8. Then 3, 4, 5, 6. I ran out of some room, so I need to go back in and fill in those little scoops the 4 zeros that we now need to hold those places. So my final answer is going to turn out to be, once I've cleared my zeros and I've kind of gotten everything where it needs to get, $2,480,000. Okay, now on the next one, notice we have a negative exponent. So the negative exponent does the opposite. These are going to send my decimal places to the left. So I'm going to write my 5.1 over here this time. So my decimal places now, 1, 2, 3, 4. There's my new decimal place. And again, we fill in what we just had for some gaps. Got to hold those place values. And so my final answer, and I think it's important that we do this, it's going to be 0.00051. When you're using decimals, it's really important that you make a very bold decimal so everyone knows what you are putting for your decimal point. Lastly, 4.65, we're going to move it to the left again because this time we see another negative exponent, so we know it's going to the left. So 4.65, it's going to go 1, 2, 3, 4, 5, 6, 7, new decimal point. We're going to have 6 zeros before the 4, and then our final answer is going to become 0.6 zeros, then 465 at the end. So notice we are moving the decimal point. Don't leave an answer as 0.0004.65. You are moving the decimal point to a new location. That's where they end up. All right, and the last one, we're going to do a little real life example here. A little kind of gross talking about the fleas here, but it's not the prettiest picture of something, but that is part of nature. So we have the dog has 100 female fleas. Over here, we know the female flea consumes about 1.4 times 10 to the negative 5 liters. It's important to see liters there of blood each day. What is the total amount of blood consumed by the fleas each day? Well, obviously we have 100 of the fleas times that number. So how do we put those two together? Well, there's a couple different ways. You could turn the 100 into something of base tens. You could also turn this this scientific notation, which is what this is over here, into standard form first, and then multiply. So let's do that first. If I was to take 1.4 times 10 to the negative 5 and turn it into standard form, remember that would be 1.4. The negative exponent tells me to go backwards or left 5 places and fill in my zeros. So now my new number is 0.000014. That basically tells me how much blood they consume each day. But we want to know, that's for one flea. We want to know what is it going to look like for 100 fleas. So really, you're going to take this number and multiply it by 100 fleas. By multiplying it by 100 fleas, when you multiply something by 10, it's going to move your decimal place to the right 2 places. So it's going to turn into 0.0014. And remember, we've been talking about liters. So right now it's the 100 fleas are doing about that for the liters. Now, liters, 0.0014 liters. Obviously, liter is a bigger measurement where this number is a little out of whack. I think if we were to change, we know milliliters are 1,000 for every 1 liter. So again, to convert this to milliliters, I think it would make the most sense. So I would be taking this 0.0014 and multiplying it by 1,000 to convert it. That would basically be moving my decimal place over 3 places, and now it's 1.4 milliliters. So that's one way to get there. There's other ways you could have gotten there the same way. I think this would be one that was kind of a quick and easy way to get there. Basic thing with the scientific notation is this. To be in scientific, it has to have a number between 1 and 10 times 10, always times 10. And then it's raised to both either a positive exponent if it's one of our bigger numbers, meaning greater than 1, or a negative exponent if it's between 0 and 1 to be one of our smaller numbers. If you are trying to change from scientific into standard form, if it's a positive exponent, you move your decimal to the right that many places. If it's a negative exponent, you move that decimal place to the left that many places. I think you'll find that it's pretty simple and easy and hopefully understood once you start working on some of these. Just be careful with your moving of your decimal places so that you see exactly how far to go with something. If you have any questions, please feel free to let me know, or we can certainly ask once we see each other next in class.